Turning on the recording. All right, guys. So today we're going to talk about, next topic. It's going to be agent-based modeling. This is something you could actually do within, I think, two of the proposed topics for the projects. Right, this is the approach you can use there if you want to. Okay. All right. So first of all, what is agent-based modeling? So agent-based modeling in general is a particular class of models, computational models, which is designed to work as a simulation, where it's a simulation between simulating action and interaction between autonomous agents. And within these models, you have independent agents that dynamically interact with each other based on certain rules. And the interesting part here is that very simple rules or agent behavior can generate very, very complex system behavior. And the reason for using those models is that, today real world is actually becoming very complex and interdependent. And very often, a lot of decisions being made decentralized and deregularized. And so it is very hard to model it from the sort of centralized point of view. Moreover, as we saw with, for example, models of disease propagation, infection propagation, it's actually, for some very simple models, we can write differential equations. For more complex interaction, we cannot write equations anymore. So in this case, we can go and do this agent-based modeling, or short ABM. So what's an agent? Now, an agent is sort of discrete entity with its own goals and behavior. Now, you might have exactly identical agents. All of your agents in the system can be identical, sort of homogeneous systems, or you can have a heterogeneous system where agents are different and behave differently. So every agent is autonomous and can, in fact, use the same behavior or modify. And what's important, that the decisions are all local and done by each engine independently, right? So agents can actually have internal states and can have memory if needed. And of course, you can model, people, groups, organizations, systems, blah, blah, blah. So if you look at the picture, the way you want to think about this is you have some environment and you have an agent. And the agent can perceive environment, can perceive the state surrounding the agent, and then can act based on internal rules that connects this perception with an action, right? If you think about this, this is pretty much how, like, I don't know, robots actually operating, right? In your robotic cars or vacuum cleaner, right? Now, the agent can be very simple and can have just sort of if-then rules and react easily on the, on the environment and have no memory at all. Or it can actually have memory and remember previous states, previous steps, and depending on that, choose appropriate actions. So agents can be, very simple, can be quite complex, but the key here is every agent is independent decision maker, and interacts with the environment. So within the environment, there'll be other agents. And so the state of environment will be determined by, other agents. Make sense? Okay. So the simulation by itself consists of a set of predefined user agents And that's, you know, the scientists, the experimenter have to define those agents, like the rules within the agents. The agents relationships, so how agents interact with other agents, and overall environment where things are happening, right? And there is no centralized controller or any authority exists in the system, right? So there is no sort of monitoring thing. The only thing that is centralized is a clock, which means, you know, you iterate, you go from step 1 to step 2 to step 3, etc. So the clock is ticking, and then every agent on each step, on each, you know, sort of clock, on the click of the clock, does something. And then, you know, agents can interact locally. So typically it's with a sort of with whatever, however we define the interaction. And then so we can monitor what's happening with the system as a whole. Now, you can think about various topologies of interaction between agents. It can be, you know, free space, it can be a grid, it can be a network. And again, the example for virus propagation is those agents on the network. It can be you know, geographic information system if you want to model road networks, etc. And then, you know, when you look at the system as a whole, then you can do some sort of some type of optimization. You know, again, examples where you prefer to do agent-based modeling, where, and I would say examples where you just cannot not do it is traffic, right? So if you want to analyze how traffic behaves, especially with traffic lights or intersecting streets, you know, there is like no good physically based model that can do it. What you do is you actually simulate this with you know, agents, where an agent will be a car. So when do we want to, you know, do this agent-based modeling, right? When there's like sort of natural representation. So when decisions and behaviors can be defined, you know, discretely for each, you know, for each agent, right? So you're actually describing the rules for an agent. Again, in a simplistic world, you know, agent will kind of keep its own behavior, but you can make it change behavior, and agents can actually learn as time goes by. In effect, this sort of reflects to like reinforcement learning kind of approaches. You know, the agent during the time can actually form and dissolve relationships, right? So can interact with other agents and then stop interacting, and then think about, again, network and time-dependent network where the agent appears and disappears. And, you know, quite often agents have this spatial component, right, to their behavior. Now, what's extremely important, you know, when you use these agents is when, you know, the past is not a predictor for the future, right? In some sense, it just tells you right away that sort of machine learning is not going to work in these scenarios, right? Where the past does not completely define your future. And so that's where the simulation is really shining. Now, you can actually, with the agent-based modeling, you can, you know, scale it up easily. You know, you can put thousands of cars, millions of cars out there in a simulation, and you don't care, right? It scales linearly. And the interesting thing is, you know, you kind of monitor how things evolve, and you might see, you know, the global change of the behavior of the system, you know, the behavior of the system, depending on little changes, you know, in behavior of every agent. And for example, you know, you can try to change the behavior of every driver and limit the speed of the car, just put the certain speed on the cars, or you know, change the length of the traffic light signal, and then all of a sudden you observe that your city either moving or stuck in a, you know, complete traffic jam, right? So that will happen, this phase transition will happen depending on simple change of the rules of the behavior of every car. right? It can be up to the point of like, you know, I will allow, you know, 1 meter distance between bumper to bumper versus like 3 meters. That can actually change the formation of traffic jam on the freeways, right? So like sort of local interactions can change the global performance and behavior. Now, what we're going to do today is, this is sort of quite conceptual. What we're going to do today is we're going to look at a very famous sort of agent-based model. In fact, you know, when Thomas Schelling is Nobel Prize winning economist, when he wrote this model in the 70s, you know, he wasn't thinking about this as an agent-based model. In fact, this sort of agent-based modeling didn't exist there back then as a sort of as discipline. But what he was thinking more is from economics point of view, and sort of his famous book and quote is this: micro motives dictates macro behavior, which really means that sort of local action of every person, though they're independent and they're local, as a collective, sort of collective action can change the behavior. You know, the local action of, you know, of everybody going onto the streets can actually, you know, flip off the government, right? So simple, small action of every person can actually have a very big macroscopic consequences to the system. And this is this change in personal preferences, you know, can lead to strong collective actions. And he actually addressed a very interesting problem, you know, the problem that today is actually going to be quite challenging even to get like funding to investigate. So what he looked for is a segregation in the cities. So we all know that a lot of cities are segregated, which means, you know, people of similar nationality, race, ethnicity, they tend to live, you know, in the neighborhood, right, in sort of enclaves, and, you know, other people will live in other enclaves. And so the question he was bringing up is like, okay, so what's going on? Because when you kind of interview people independently, nobody's really that much of a racist that they would say we don't tolerate people of different, you know, skin color or different religion in our neighborhood. But in spite of the fact that, again, most people are quite tolerant, all of a sudden, as a system, when you get the sort of the system behavior, you know, eventually cities becomes segregated, right? And so the question he was investigating is how is that possible? Every agent is tolerant, but as it results in global, you know, intolerance. And you can very easily extrapolate this, you know, findings, not, you know, to politics and, you know, a lot of other things. All right. So where every person is a good guy, but, you know, overall it's a shithole, right? So now, so what's segregation? Yeah, I think it's easy just to look at this picture. And you know, what we see on the left-hand side, if we have two types of agents here, blue agent and green agent, on the left we have an integrated pattern where blue is, you know, mixed up with green, and on the right-hand side we have a segregated pattern of behavior. So what's important is that if you look from the point of view of, you know, individual agent, and in this case a pixel is an agent, you know, mostly, you know, green pixels have neighbors on the right-hand side. The neighbors of the green pixels are green pixels, right? And the neighbors of blue pixels are blue pixels, right? So that's sort of here, the neighbors of red are red, here the neighbors of blue are blue. It's only these guys who kind of suffer that they have some of their neighbors of different color, right? So that's segregation, this is integrated pattern. All right, so, you know, the fact that racial segregation exists, you know, it's, well, it is a fact, right? And these are the maps for United States. where, you know, racial segregation is a problem. And by the way, if you're kind of watching the news, has been again a lot of tensions within the last 2 days in the US, like racial tensions. So if you look at those cities, the way it's color coded is actually black population is shown here in a gray color, white population is in green, orange. Can somebody guess, you know, the orange color? Who are these guys?
Maybe Hispanic, Latino.
Yeah, it's Latino population. And you can guess that by, for example, looking, let's say, let me move this. Just a sec. Yeah, if you're a little bit familiar with United States, then, for example, here we got LA, right? And if you look at Los Angeles, you got, you know, the rich white guys live along the ocean. Then there is pretty much LA Central, the black guys. Then there is a huge Latino population. Then there is a Chinatown here, and then again rich white guys. So you know, Seattle also has lots of you know, Asians living right here in the big enclave. Miami, again, you can clearly see, you know, rich Latina, black. Chicago, the same situation. Washington is, you know, heavily black. New York, well, you know, Russians live here. So there's Manhattan, you know, the mixed, and this is Upper Manhattan, this is Harlem here. So, and this is rich Manhattan. So there is, it exists, it's a problem, all right? And, you know, it's here, it's staying, nobody does anything about it. So the question is like, why the hell this happens, right? And especially take into account that people, you know, getting more and more educated. And so, you know, United States is just a mix of all cultures and nationalities. So that doesn't seem to, this shouldn't be a problem, right? Now, another interesting example is, this is back 2012, when there was elections, US elections, Obama versus Mitt Romney. It's also kind of interesting that there is a lot of geographical similarities here. You'll notice the regions that vote for Obama, it's sort of educated East and West Coast, you know, educated West Coast, so Seattle, Silicon Valley, you know, San Francisco, New York, Boston. And then there is this huge, you know, pieces voting for Romney/Trump these days. And if you notice, it's also very, very contiguous, right? So it's actually, you know, you literally see enclaves of people. Now, you can also think about it, you know, maybe living in the same place makes you vote the same way, or maybe you just actually don't want to live among people with very different political preferences. And that's actually quite true. So people move because of political preferences of their neighbors. Okay, so there you go. Let's model this. We're going to follow Schelling's original paper. By the way, I would strongly recommend you to read it. It's actually, you know, amazing. This is like, you know, 50-year-old paper now, but it's well written. And this is a topic that today people try to avoid discussing. So back then it was, you know, you could just write it and it was fine. So population consists of two types of agents. And the agents reside on a cell of the grid. So remember, you need to introduce some sort of geometry. In our case, we'll be talking about this two-dimensional geometry. And you know, every person will have 8 neighbors. So for those of us, you know, who spent childhood on dachas, it's kind of one of those scenarios. You have a neighbor to the left, to the right, up and down, and a diagonal, right? So it's kind of in a grid. And every agent wants to have at least some fraction of agents. So every person wants to have some fraction of neighbors of his type. And if it happens, agent is satisfied. And so it does nothing. And if it doesn't happen, if an agent is unsatisfied, it moves to a new cell, right? It tries to find a new cell where it can be happier. Of course, for this to work, there should be some empty cells available for allocation. And then this process continues until it kind of settles down, right? Make sense? Okay. So this is an example. So we have this sort of grid structure. Our agent is here, is X. In the center, empty white box is an empty spot where agent can move. And these are two different types of agents, red and black. And so here is, we have, let's say the agent X has a preference threshold of 3/7. So what it means is, you know, out of 8 neighbors, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, right? So, you know, for this agent, and, you know, there is one empty spot, so it's 7 possible neighbors. For this guy, you know, 3/7 is his preference threshold. And so when there are 3/7 of his people around him, you know, he's happy and is not moving. And unsatisfied agent is the one that here, right? So for this guy, out of his neighbors, there are only 2 of his type, not 3, right? And he wants to have 3/7 to stay. So this agent will move, but unfortunately in this particular scenario, he doesn't have a place to move, because if he moves to the spot 7, it's even getting worse. Now, you should remember, we talked about, we had quite similar discussion on this thresholds when we talked about the model a couple of weeks ago, right? There was this cascade model when we also looked at the thresholds and number of neighbors to change the behavior. So that's where the roots of that sort of logic sits. Now, this is the actual figure from Thomas Schelling paper. So he didn't do computer experiments, he did it by hand. So he introduced those rules and, you know, looked at how things will change following them. By the way, guys, have you heard about this game, like, was popular back in, I don't know, long time ago, Game of Life? Yes. So that's pretty much what it is, right? So you have agents, and you know, depending on the configuration, there are some rules, and that's the way agents behave. So what happened is, when you start with some sort of distribution here, after several iterations where you literally go one agent by agent and see, okay, if the agent is happy or not, right? And if he is not happy, if the agent is not happy, he can move to some place which is available, right? And then it just keep going on and going on and going on. What happens is, eventually, sorry guys, some crap. So what happens here is, you know, eventually you get where the circular guys get together, right? And the other guys also kind of get together. And so you have now, all of a sudden, those separation, okay? Okay.
Sorry, I have a question. So how it's work? I mean, it seems like if we it's important order which agent make a decision.
Yes. So it is important, and you might end up in a different state, you know, if you change the ordering. That's absolutely correct. But the point is, you know, eventually what you do with this type of models, right? You run the simulation many times, and since, again, you will see there is a lot of randomness in here anyway. So it kind of, you know, averages out when you try to calculate eventually statistics, because what might happen is if you run this simulation once, you get this, right? You run it, for example, starting from this agent, you will end up with a very different picture. You run it one more time, you might end up with a very different picture, because in every step, and I didn't say that yet, but on every step when the agent makes a decision to move, there is very many places he can move to, right? And so then, there are several, several strategies. It can try to move to a place which is sort of the best place, or the emptiest place, or the nearest place, or pure random place, right? And so that's instantly gives a lot of randomness.
And for computer science people, there's so agents can activate on a certain step in a certain order, but they can also randomly activate. So activate in a random order is I thought it was my internet that died.
All right, I think I'm back. Can you hear me?
Yep.
All right, I don't know what the hell is happening today. And I need to share screen again. Can you see the screen?
Yeah.
Yeah.
Okay.
May I ask a question
Yes, of course.
about this? So, is there, does the degree of satisfaction like matters? For example, the guy wants to have 4 neighbors, but now he has 1, and there are no places where he can get 4 neighbors, but there is a place when he can get 3 neighbors. Will he move, or it doesn't matter for him 1 or 3 because it's less than 4?
So the way it is, sort of the original paper, the original sort of Schilling's, spatial segregation model, it has like, very simple rules where it is sort of yes or no threshold, right? But you will see in a second that you can easily, relax those rules. And if you make a computer simulation, you can, pretty much put any rules you want. You can, instead of utility function that is binary, 0 or 1, sort of satisfied or not, you can make utility function that growth, the dissatisfaction growth proportionally to the number of neighbors, for example, right? And then run the simulation. So original paper, it's binary, but you can do whatever you want with it.
Thank you.
Okay, so actually this is where we want to discuss this now. So n is a number of nodes. Theta is a fraction of occupied nodes, right? So we want to have some empty spaces so the nodes can move around. A number of nodes of type A, or agents type A, and number of agents type B, that's a fraction of, and altogether they constitute all the agents that we have in the system. And n is a number of sites, right? So you, again, within this model, you calculate the proportion of nearest neighbors, nearest neighbors that are, of the same type and of the opposite type. It's actually, I'm sorry, you calculate the proportion of unlike nearest neighbors, right? So For node type A, it is a number of B type of neighbors. For node type B, it's number of A types neighbors, right? So proportion PI is a proportion of unlike you neighbors, right? Or neighbors you don't like, or the neighbors that do not look like you, right? And then there is this utility function. So within Schelling's model, this is sensitivity, tolerance threshold. And if your nearest neighbor's proportion of your nearest neighbors that unlike you is below threshold, you're a satisfied agent, utility function is 1. If it is above the threshold, unsatisfied utility is 0. But as I said, sort of that was the original paper. You can change it to whatever you want. And then pretty much on every step, every agent moves to maximize utility function. In this case, utility function is binary. So like all empty locations, you either will have equal utility for the agent. I mean, if it satisfies the constraints. So what's interesting is here is like already simulations, right? This amazingly, this simplest set of rules, if you look at the system, there is really no analytical solution to this. And these are simulations. Here is a simulation where the it's simulation on the grid, right? Here's a simulation where vacancy is 5% and tolerance is 50. And then there is just number of steps. So you start with a completely mixed up situation, and then 10 steps, you start seeing this, 100 steps, you're seeing this, 400 steps. Wow, right? It's completely segregated. And the rule is very simple. So this is actually quite tolerant population, which says, look, I'm happy if half of my neighbors are not of my type, right? So this is quite tolerant. But that leads to segregation, though each person is, more or less tolerant. Now, here is like a bunch of other experiments done with a different density of, empty spaces, right, of availability. Different thresholds selected here, but you realize that still there is sort of quite strong, and in fact, it's phase transition that happens right there and right there. So what we see is when your threshold is when you're very selective, you cannot move because there is no good place for you, right? Let's say if I want to have a very low threshold on people unlike me, right? Very low threshold here. Again, let's say, oops. If I go back here, right? So threshold is, this is a percentile of people unlike, right? This is a percentile of people, of neighbors unlike you. And this is a threshold, right? And if it's percentile less, I'm trying to make sure I'm not mixing it up, right? If the percentile of people is below the threshold, you're happy. If it is above that threshold, you're not, right? So if the threshold is very low, it means you are not tolerant at all. You don't want to have anybody not like you in your neighborhood, right? And so what happens is when somebody is extremely intolerant, like the entire population is extremely intolerant, then there is really no place to move, because whenever you move, you will still get somebody of not your type. And in some sense, at this end, the system is sort of frozen, right? It can, there is no way to move. Here on this end, everybody is very tolerant, right? Says, I don't care at all. And then there's a good mix up. But then there is this, so it's kind of famous for this model. There is really 2 phase transitions and 3 phases, this 1, 2, 3. phase number one is sort of the frozen phase where you can barely move and it's preserved mix-up. Then there is an opportunity to move. You instantly get segregation, and then when you're sort of happy camper no matter what, yeah, then you can again get a mix-up. So then the question is sort of where are those boundaries, right? And of course, they do depend on the number of vacant things. They do depend on the preference functions, but what they also depend on is they depend on the geometry of the problem, right? The original problem, the original Schelling problem, was set up on this regular grid, right? But you can actually think of very different geometry, and you can use network to model it, right? And it doesn't have to be necessarily like nearest neighbors. It could be your coworkers, right? You model, and in fact, you also see huge segregation in, like, for example, in Silicon Valley in companies. Like literally, you'll have divisions of Indians, you'll have divisions of Asians, you'll have divisions of Americans. So it is noticeable. So you can actually, depending on the network, you can actually model this on the network, right? So how you model this? Well, pretty much as we discussed, a very, very simple model. You turn on the clock, and there are time steps. And at every time step, you randomly select an agent, or you can just go one agent. You randomly select them until you go through all of them, or you just sort of choose one sort of way to go through all of them. And then if utility of the agent is 0, which means this is unhappy agent, you move to an empty location to maximize utility. And this movement could be like a random location or nearest available location or whatever you decide. And then you just repeat. And then eventually what's going to happen, you either get to the state where, where motion stopped because everybody is happy, or, and then utility is maximized, right? Pretty much this formula, right? The sum of utilities is equal to the fraction of all occupied nodes. And if whatever its agent A or B type, if it is happy, the utility is 1. So if the sum of all utilities is equal to the fraction of occupied nodes, which means every single node is happy here, right? So then all utilities maximized, you reach the happy state. Or it can be a sort of what's called frozen state situation, where the sum of the utilities is less than possible, but the system cannot increase them because just because there is no empty spaces, right? And then you can actually instantly talk about all kind of sort of econometrics and economics, stories about the utility for of the society. If you think about utilities of each individual person in the situation.
May I ask?
Yes, sure.
Does the third state is always in a constant move, or it's also frozen actually but satisfied? I mean, the third phase where you had 3 phases.
This one.
Yes.
Right. Yeah. So when you get to this phase, eventually, if see what we do, if utility is where is it? If utility of agent is 0, move to an empty location, right? So if you reach the situation when the utility of every person is 1, then all the movement stops, right? Now you can be in a scenario where like 99% are 0. I'm sorry, 99% are 1, and one sort of person is 0. Well, then it's going to get frozen because the person will try to move around, and there is no way to move around, right? So eventually, if you think like limiting scenario in this picture, if you go way right, which means everybody's 100% tolerant, then you kind of reach happy state right away. right? Nobody moves. Make sense?
Yeah, I see. Thank you.
Okay. All right. Now, one last thing we need to do is, when you have this type of models, you want to understand, you want to distinguish those states, right? So we can look at those states and just see how different they are, or we can measure, like put a metric of how this mixing happens. And there were a bunch of indices. One of them, again, Schelling proposed his own index, what's called solid mixing index, which is 1 over the number of, well, pretty much the total number of agents, and this is the sum of their preference function. So if, for example, go back to the definition, it's proportion of unlike nearest neighbors. If you don't have any unlike nearest, if everybody does not have any unlike nearest neighbors, then this proportion, is 0, right? So that's this mixing index is 0. Now there is a segregation index, which literally says how things are segregated. So what you do is you just count how many edges are within the group, right? So in between the nodes or between the agents of the same type, and how many of them are in between different types. And if you remember, we talked about the assortative mixing for clustering. That's pretty much the same situation where you try to calculate the number here, and it's 1 within the summation if it is the same class, and 0 if it is not the same class. So you can use any of those metrics. And if we want to model, precisely, exactly try to model, Schelling's model, then we need to have this type of a grid, right? Where for every node, there are 8 neighbors. But you can also do it on, any network. And in fact, for a long time, there was a discussion that Schelling's model is very robust to geometry, right? So whether you take 4 neighbors, 8 neighbors, it still pretty much shows the same behavior. So this is a paper, and if you notice, Schelling's model is 1970. This paper is 2010, where the researchers decided to actually run Schelling's model on networks. Now, they wanted to look at, regular grid. They wanted to look at scale-free network. They wanted to look at the random network, I think, and they wanted to look at this sort of, Sierpinski gasket, what's called, this fractal types of network. Now, to make the comparison, meaningful, since each of this network has different number of neighbors, and within the model, there is sort of you're always talking about the fraction of neighbors. So they kind of remodel those networks by forcing every node in the network to have, the same number of neighbors, right? But preserve the connectivity. So the properties, remained in terms of small world and more or less distribution. And so here's the results from what they're seeing, right? So they ran, for example, for the filling factor 80% and the threshold 1/2. And of course, they observed, the formation of, those, segregation, right? The regions that segregated. And if you notice, obviously, you got the sort of, if you see here some sort of clusters, right? Some sort of denser parts, they actually got segregated, right? And here it's very clear that the whole thing here is segregated, those 2 clusters here, those clusters. So the difference between the network on the left and on the right, right one has like quite a few clusters, right? So it's a high clustering coefficient. The network on the left doesn't have clusters. And here's what they observed. Tolerance on the bottom, and the level of mixity is on this vertical axis. So what you have here is, mixed population, segregated. So we got like population, gets segregated, strongly segregated, somewhere in between, 30% and 70% threshold, which is actually quite similar to original model. But what's interesting is there is quite different behavior in between, say, so grid and random network, they look quite similar, right? And grid is pretty much what's happened, it's pretty much the model that the original model. And, those two networks, scale-free and Sierpinski, those that have clusters that behave quite differently. For them, the level of mixity, or another way, the segregation becomes much, much stronger. So clusters do kind of encourage segregation, right? The existence of the clusters. And in some sense, it's kind of understandable, because cluster is, right, is a subset of nodes that are tightly connected. And so when one, black person moves into the cluster, eventually it instantly gets lots of neighbors around it, and, it will push out everybody else from that cluster. So, the scenario is that here we got, again, high tolerance, which means these are sort of happy people, right? It is mixed up and people happy. Here we have low tolerance, but strong mixity, which means they're unhappy people, right? They have low tolerance, they would like to move, but they just cannot. And then what's striking is that with 50% tolerance, which means each of us, you and me and everybody else on this call, happy to have half of the neighbors of our type, and even 60% if you agree for like 6 out of your 10 neighbors to be of your type, which is like, okay, I'm more than tolerant, right? I agree more than half of the people around me to be, more than half of the people around me to be of a different type. All of a sudden, it will still cause complete segregation. That is actually a very, very powerful result. Now, what's also interesting is guys actually made one more experiment when they said, okay, look, our agents were very stubborn and they just, strictly followed the rules. What if we add a little bit of noise, which means, the decision will be less, so sometimes they will kind of decide against the rules, right? Sort of 10%, they added 10% of noise, right? So what they wanted to see is how, stable the results with respect to noise. And they realized that, that on the one hand, again, grid and random, sort of in particular, sort of grid, which literally is the original model that was out there. Yes, it's still the same scenario where at low tolerance, everybody is stuck and unhappy and it mixed up. But for scale-free and Sierpinski, when you grid is stuck even if you allow a little bit of sort of random decision making. But cluster-based models, they instantly get segregation for us, like instantly. So if you get a little bit of decision making that is to the agent that is allowing to violate a little bit rules, because remember, you can violate rule, you can move to some location which you're not happy with, and the move next, sort of kind of strategically thinking that you next time can move further, right? I mean, not strategically thinking this agent do not have any strategy in them, but kind of allow this. This is why this is done. It's, if you're familiar with optimization technique like simulated annealing, right? The notion is trying to avoid getting stuck in local minima. And so that's pretty much what's done in here. And then you see that there is a huge difference at low tolerance in between, sort of regular grid random and networks that have clusters in them. So it looks like this effect is due to, clustering, which actually tells you that from the point of view of kind of city construction, if you're building those, now if you think about roads and you're building those small enclaves separated by freeways, they completely enhance, like they encourage this segregation, right? So that actually this ideas can and should affect the way cities are built, right? Trying to avoid sort of clusters in terms of construction things as much as possible. So if you have like what they build in New Moscow, right? Bunch of buildings next to each other, like small cluster, then nothingness, then another small cluster, then nothingness, then another small cluster. They're forcing segregation. And that's going to happen, and it is happening actually. And so, this model actually shows it. All right.
Sorry,
So, yeah.
This noise decrease over time, because otherwise it means that we have not stationary point in the final case.
I'm sorry, say it again.
So this noise, random noise, decrease over time or not?
Here they just set up like 10% random noise. I think they just edit and not decreasing it through the entire simulation. So through the entire simulation, agent could make the move against their rules in some sense, right? That's what this 10% means.
So in this case, it could be strange, because in this case we have no, like stationary point. So I mean the agent will be moved infinitely. Why we have just final picture?
Yeah, it's possible that within this model you don't have. I mean, even here there will be still some sort of motion continue, right? It's just not going to change the too much the sort of the happiness, or it might the happiness might sort of fluctuate, right, because of this noise. But it's not gonna it's not destroying. I mean, look, I'm pretty sure if you add like 50% noise, you'll get a very different behavior. I would refer you.
Is the noise supposed to factor in to be the means by which you factor in external things you can't control?
So noise here is sort of remember, every agent make a decision, sort of logic decision, move or not move based on the neighbors, right? And so what this noise does is it just says sometimes you don't kind of follow this rule, and you move when you shouldn't move, and you don't move when you should move, so to speak, right? But if you guys want to know more details about this noise thing, check out the paper. It's available online, right? So you can read through the results, detailed results, how they actually did the experiments. Look, I agree. Let's say, for example, if you do simulated annealing, right, and that's sort of the temperature over there that you add to optimization, you actually as you go along the optimization, you kind of decrease it, right? And so that makes things converge to stationary situation. I think they did not decrease it here, and that means you're right. There's still some motion on this on this part of the spectrum, even there, but maybe they did. So need to check. I think, I mean, probably good point that you might kind of drive it to zero after some number of iterations. Okay, the good news though is that since this is very simple sort of model that drives this kind of very unusual behavior of segregation, right? And segregation taking place even though in sort of there is a there are two sides here. One side is a sort of sociological economic consequences, right, of this paper and the model, that you do have this segregation and it takes place, it doesn't matter that individual agent is not actively seeking it, right? And have not high enough tolerance, it still leads to segregation. and the network does affect this, right? So, and pretty much the sort of the final conclusion is that those characteristics that are sort of immutable, like, you know, for example, race, becoming correlated with those things that can change, that are mutable characteristics like location. That's sort of the result of the study. But from the point of view of, like, you know, computational approaches and methods, this is actually a very, very powerful, you know, approach of agent-based modeling that can be used, like we discussed, you know, trying to model propagation of diseases. Sort of, it's actually easy to build those type of models, and there are a lot of control parameters that can easily put in yourself. So and it's usually used where you cannot really easily you know, predict or write down equations. For example, if you want to simulate, you know, the behavior of the market, you can actually write lots of trading agents in this type of fashion and see how they behave, and you can have like very, very different you know, logic and very different strategy for each agent. And then this is going to be agent-based, you know, simulation. You're going to see what's going to be happening with the market, right? Or, you know, the other place is the traffic modeling of the traffic congestion in the city, also done through this. And there's sort of no good ways to write equations there. And you can come up with many other approaches. And right now, I think, you know, people do try a lot this type of simulation for COVID to understand how the measures that government takes, like local measures, affect the spread of the disease, because no other model can take this into account, right? Like sort of lockdowns, temporary lockdowns, how they actually affect the overall spread of the virus. Okay.
I have a question.
Yes.
Can I show a very short demonstration is this simulation?
Absolutely, but do I need to somehow share screen with you, or you can just take it yourself? What do I need to do? Do you know?
You need to allow guests to share their screen.
I click on the screen share button, but it doesn't work.
You need
so
to
give me one second. I need to allow somewhere.
Yeah, so there's a share button with an arrow at the top. You click on it and then you allow guests to share or other people to share. Then they'll be able to share their screen.
Just give me 1 second. It says advanced. It doesn't. In my share button, it doesn't say it. But by the way, if you try to share, can you? So I'm not sharing anymore anything, right now.
No, you continue sharing. No.
I'm continuing sharing.
Yeah.
This is weird. Okay, let me do this. So okay, I stopped sharing.
I'm clicking on the button and I see организатор отключил демонстрацию экрана участников.
Okay, let me see if I can turn it on. Okay. Okay, can you try it now?
Yep. Do you see my screen?
Yes.
And this the high threshold, and there is no stable state. But if we will decrease, then we see something like that.
Yep.
Yeah, it is.
Yeah. And if you take it to very low threshold?
Okay, let's try to.
No, the other way around. The other way around.
Okay.
Yeah, that's any logic. Yep.
Yeah.
Do you write in any logic, or did you just grab it somewhere?
Can you repeat?
No, did you write this code yourself, or is it like demo from their site?
Demo from the AnyLogic.
Their site, from AnyLogic, yep.
Yeah.
Yep, so what happens now, it's a frozen state, so probably they cannot move because each of them is too picky, right? So the tolerance is too low, and then if you start moving, we should get to the point where they are moving. Yep. And there are more and more, and then we will, and probably somewhere here, if you wait for a minute, we'll get, yeah, just keep it there. We should already see the segregation here, and we're already seeing it. Yep. And then, the very end, yep, it's getting all mixed up. All right, good, thank you. Thanks for the demo. All right, guys, any other questions?
I'm curious, when we were talking about different models, you said that anyone in these 4 models where we have Sierpinski triangle, all of this stuff, everyone has 10 nearest neighbors. So you mean that each node is of degree 10, right?
That's a good question. I think they I think they wanted to make it each node of degree 10, but they wanted to preserve the sort of locality, right? So the question is, when you increase this to degree 10, how do you make those connections? So do you connect to like next nearest neighbors, or where do you pick up those additional links, right? So the answer is I don't know. Need to look up. I do remember that they they kind of equalize networks in this sense, right? So the reason is they wanted to, since the simulations are designed to count the fraction of nearest neighbors, right? If you have very different number of nearest neighbors, it's probably you're not comparing sort of apples to apples, right? And so that's what they did. But precisely how they did it, I honestly don't remember. Take a look at the paper.
Yeah, it just seems strange, feels strange that we have a scale-free network with degree distribution of constant, like everyone has.
No. I don't think. Yes, that's what I'm saying. Yeah, it's strange if how they set this up. It's possible that they wanted to have a minimum 10 neighbors. But then, there will be some nodes with a very, very high degree. I think it would be good, guys, if you take a look at this, and then that of you who actually find the right answer, send it please to everybody, right? So the paper is on the slides, on the last slide. I'm not sharing it anymore.
I was reading the PDF and I wasn't able to answer for sure, but they use some algorithm to connect to the 10 nearest neighbors, the 10 closest neighbors.
10 closest neighbors, right? But then they completely destroy the power law.
Well, yeah,
right?
I guess, but
which is surprising, right? And their network looks like they still have a power law. So let's read and see what actually they have done. All right.
Yeah, thank you.
Okay, and I do have I'll put the slides online so you have a reference, and then I'll wait for whoever gonna explain how they did it, right? For extra bonus points.
okay.
Right.
I'm just read, but
yeah,
I have a
really
question not related to this lecture. Okay, but it's not related to this lecture, but I was reviewing diffusion on graphs. And I mean, I really would like some example problem or something, because I see the formulas and I'm like, okay, second eigenvector should be, eigenvalue should be this and stuff, but like it's all going to fall out of my head, and it's not material in Barabasi, so I don't know where to look. Like, is there like a small example problem?
Okay,
Graphs?
Okay, I'll take a look. We'll find something where there is, yeah, with some examples for the diffusion on graph. Okay. All right, guys. All right, so we're done then, and have a good weekend. Stay safe.
Thank you. Goodbye.
Thank you. Goodbye.
Bye.
Thanks, especially for this lecture topic. Bye.
Bye-bye.